8.2 is about buffer solutions. A buffer is something that acts to reduce the impact of one thing on another thing. In chemistry specifically, we look at the fact that buffers are resistant to changes in pH based on the addition of small amounts of acids or bases. The key term here is small amounts. So if you dump a lot of acid or base into a solution that has a buffer, it still does not, or it will no longer have the buffering effect. It only has an effect for small amounts. Where this is important is ocean water, as an example. So ocean has a pH around 8 to 9, so it's actually considerably basic. And it's controlled by several buffer systems. The carbonate and hydrogen carbonate ions exist in equilibrium, and they are crucial to the buffering action of the ocean. The ocean has the capacity to absorb huge amounts of carbon dioxide from the atmosphere, so it is what we call a carbon sink, which is very important in helping to alleviate the effects of increasing atmospheric carbon dioxide. But as carbon dioxide dissolves in the ocean, it makes the water more acidic, releasing hydrogen ions that shifts the equilibrium above and reduces the concentration of carbonate. Coral reefs are directly affected by this, as they depend on the carbonate ion to build their structures and have shown serious decline with decreasing carbonate levels. Of potentially greater impact still is the fact that the decrease in pH of the water may set up a feedback loop, reducing the ocean's buffering capacity and so diminish its ability to take up additional carbon dioxide from the atmosphere. Many research scientists believe that ocean acidification is potentially the most serious of all predicted outcomes of increased atmospheric carbon dioxide. Another example is the human body. We have a lot of buffers in place, which is why when your body temperature gets above its core temperature, let's say 98.6 degrees, even to 99 degrees, our body goes into a fighting aspect in which to try to break the fever and counteract it. There's a lot of buffering systems in our blood, so on and so forth. So buffer systems are used everywhere, and they're there to make sure the systems that are running safely in the way in which they're supposed to run. How do buffers work? The first things we need to look at or focus in on are we need to focus on the equilibrium equation that occurs in the solution. Then we need to pick out a species that will either respond to the hydrogen ions present or the hydroxide ions present. There are two types of buffers, acidic buffers and basic buffers. Acidic buffers, in their composition of the buffer solution is you mix a weak acid with the solution of its salt with a strong alkali, like sodium. So an example of this would be here we have acetic acid, CH3COOH. It breaks down into COO minus and H plus. That is a weak acid. Its salt with a strong alkali is sodium with CH3COO minus. Therefore, when you look at this, the solution contains a high concentration of both the acid and the conjugate base. So here we have our acid. Here we have the conjugate base provided in both of the reactions. Buffers are considered reservoirs, and they are ready to react at any point. And so we would have a solution with the salt and the weak acid here, and no matter what we put in, if we put in some more base, if we put in some more acid, it will respond accordingly. What does that look like? When you add hydrogen, the conjugate base reacts with that hydrogen to reproduce more acid. If we add hydroxides, our acid reacts with more base to produce a conjugate base, so on and so forth. What we have to keep in mind with the way buffer systems work is we have both the conjugate base present and we have the acid present to take care of the hydrogen and hydroxide ions. As you are adding acids or you're adding bases to the solution, those hydrogen or hydroxide ions do not persist because they have the ability to react with either the acid or the conjugate base. Therefore, we do not see a pH change when a buffer system is in place. Basic buffers. Composition is similar, just looking at bases instead. The composition is a weak base with a salt of that weak base with a strong acid. Looking below, our weak base, we're using ammonia, NH3. When that reacts with water, you get NH4 plus and OH negative. Here we have the salt of a weak base with a strong acid, chlorine. So here we have NH4Cl, breaks down into NH4 plus and Cl minus. So once again, we have our conjugate base acid pairs where we have our weak base present and then we have our conjugate base acid pair to that base. And so no matter what we add, we have the ability in which to buffer acids or bases. What do those responses look like? If we add hydrogen, we're adding hydrogen, so our weak base then will react with that acid to create NH4 plus. If we add hydroxide, the conjugate acid reacts with the hydroxide to give us our weak base back. And if you're noticing here, it is a cyclic process where this conjugate acid can then become what is needed to react with the hydroxide ion. And when that happens, we reform the base that would need to be there to react with the hydrogen ion. And that works with the same way in our acids as well. Determining the pH of a solution. There are a couple assumptions we need to make. 1. The dissociation of a weak acid is extremely small, as we had talked about in 18.1. Therefore, the concentration of your initial acid is equal to the concentration of the equilibrium acid. This is called the common ion effect, where the presence of a common ion, like the dissociated acid, suppresses the ionization of a weak acid or base, or reduces the solubility of the salt. Second, the salt is considered fully dissociated because it is a salt and dissociates in water readily. Therefore, we are looking at the metal alkaloid. So we have our acid here, the salt of the acid. That initial concentration is going to equal the acid at equilibrium. What is this needed for then? Here we have, looking at acidic buffers, we have our acid dissociates into the protons and its associated conjugate base, or the ion version of the acid. Here we have our alkali metal with the acid, so M, sodium, and that fully dissociates, hence the single arrow, to the metal ion and the associated conjugate base. So as we noticed before, here we have the conjugate base we need. Here is the acid in which we need to run a buffer. Because these are weak, we have to look at the Ka values. Here is the pathway in which to set this up. Ka equals the concentration of your hydrogen ion times your acid ion over your acid, as we saw in 18.1 again. If we are trying to isolate our hydrogen ions, because that is specifically what we're looking for, is the concentration, so we can go to pH, just manipulating the equation, we have our Ka is multiplied by the acid. Now remember from the previous slide that the initial concentration of our acid is the concentration of the equilibrium acid because of the small Ka value. On the bottom we have our dissociated acid from our metal. Because we're assuming full dissociation, the concentration of the salt acid we had put in will equal the concentration of the conjugate base in this situation. Therefore, to make it a little bit easier, we say the concentration of hydrogen protons equals your Ka times your acid over your salt. We rearrange that and take the logarithmic scale. So now we have pH equals pKa plus the log base 10 of your salt over your acid. Now, the majority of time, this value is going to be the same number because that is the way in which the base works. Therefore, we don't usually need to worry about it, and our pH will equal our pKa. Without doing all the work, just keep in mind that pOH will also equal pKb plus the log base 10 of the salt over the base. It is the same setup, just working with a basic buffer instead of the acidic buffer, but we have both calculations present. Now we have an example in which to work using this problem. So if we have 25 centimeters cubed of a 0.1 mole per decimeter cubed solution of CH3COOH, so here is our weak acid, and we have 25 centimeters cubed of a 0.1 moles per decimeter cubed of NaCH3OO. Here's the salt to our weak acid. The Ka value is 1.8 times 10 to the negative 5 at 25 degrees Celsius. Remember, we need to know that it's at 25 degrees Celsius, otherwise that Ka value is affected. All right, we just looked at the calculation which we want to perform. Here we have A. So we are going to have our pH equals pKa plus the log base 10 of our acid over, not our acid, our salt over our acid. First, we need to get our pKa, which means we want to take the negative log base 10 of the Ka value, 1.8 times 10 to the negative 5. When you do that in your calculator, you get 4.74. Now we can enter in this information. pH equals 4.74 plus the log base 10 because all our information is appropriate up there, same concentrations, same volume. It is a 1-to-1 ratio, which when you take the log base 10 of 1, you get 0. Therefore, our pH equals our pKa of 4.74. And that shows you that our base or our buffer solution, and the pH in which it runs at is 4.74, and that is what it's being designed for. So how do we go about making these buffer solutions? First, you want to start with the weak acid or base that is close to the wanted pH. Like in the previous example, our buffer solution had a pH of 4.74. That means we are working with a solution that had a pH of 4.74. The second thing we want to look to is react. We want to react with a strong acid or base, so half is going to be converted to a salt. Looking at an example here, and this is just using pretty little whole ratios, so it's not confused at all. But looking at what happens here, okay, so we have CH3COOH. That is our weak acid. We're reacting it with a strong base, so we can make our salt. So now we have our salts, we have our weak acid. We want to make sure that half is being converted. Therefore, if we have a grand total of 2 of our original concentrations or moles of our weak acid being used, half of it needs to go to a salt. Therefore, we are going to change everything by half the original amount, which is 1. Therefore, we have an equal number of our salt and our weak base, our salt and our weak acid. The same thing could be done for a strong or a weak base done with a strong acid. How can we influence buffers and their effectiveness? One way is dilution within dilutions. So our Ka and Kb value do not change with the dilution. Those are only affected by temperature. Nor is the ratio of your acid and base to its appropriate salt. Therefore, pH does not change. However, what does change about a buffering solution is what is called the buffering capacity. A buffering capacity is the ability in which the buffer can absorb hydrogen or hydroxide ions. Because there's less buffer present, it has less ability to control any kind of change that exists. Therefore, diluting out the ocean with the influx of fresh water from the melting ice caps is diluting its buffering capacity. Therefore, it's turning more acidic, which then has that downward spiral with not being able to accept any more CO2, increasing atmospheric effect, that positive feedback loop we had talked about previously. So buffering capacity is really important. As we know, because we're working with Ka and Kb, temperature does have an effect. We have to know the temperature in which we're running. And usually pre-made buffer solutions have what temperature they need to be made at and are controlled at. Otherwise, they're not going to work to what we expect them to do. When we change temperature, then we'll change the pH of the buffer solution, and it won't work as well as we originally had thought.